scanner at the grocery store or, medical procedure, even just that little red dot your cat loves chasing. They all seem so straightforward, right?
Yeah.
Just this precise, coherent beam of light. But have you ever stopped to think about the sheer complexity humming away underneath that simple beam? Today, we're taking a deep dive into standing waves and laser resonators. And honestly, this is where the physics gets really interesting. It's fundamental to how lasers actually work. We'll be focusing on these stationary wave patterns. Our mission really is to give you a shortcut to understanding why these standing waves are so critical, and also the big challenges they create for laser performance, plus the, frankly, ingenious ways engineers have figured out how to handle them. We've dug into sources like an in-depth analysis of standing wave phenomena, quite a title, from fundamental principles to advanced performance control. We think this will give you a totally new angle on something you might encounter all the time. Okay, let's unpack this. It's a fascinating world. And we're joined by our expert guide to help connect the dots.
It's great to be here. Standing waves are, well, they're fundamental across physics, and lasers are just such a perfect example of their importance.
So let's start right at the beginning. When we talk about a standing wave, what is that? Because it sounds like it's not really moving anywhere.
That's exactly it. A standing wave or stationary wave, it isn't propagating like, say, ripples on a pond. It's a fixed pattern of oscillation. It happens when you get interference between two identical waves, same frequency, same amplitude, but they're traveling in opposite directions. It all comes down to the principle of superposition. You just add the displacements of the two waves at every point.
Like a guitar string. That's the classic, right? That always helps me picture it.
It's the go-to analogy for a good reason. Yeah. Imagine sending a wave down that string. It hits the fixed end, reflects back, and that reflected wave starts interfering with the waves still coming down.
Right.
At certain points, a crest from one wave meets a trough from the other consistently. They cancel out, perfect destructive interference. Those points, they stay completely still. Zero amplitude, we call them nodes. And the distance between two nodes right next to each other, it's precisely half a wavelength, lambda over 2.
Okay, so nodes are the quiet zones, no movement. What about between them? Where's the energy or the action happening?
Right, that's where you find the antinodes. Midway between any two nodes, you get the opposite. Crests meet crests, troughs meet troughs. Maximum constructive interference. So these points oscillate with the largest possible amplitude. And just like the nodes, the distance between consecutive antinodes is also 2. Now, a really key thing about the phase. All the points in one loop between two nodes, they all move up and down together. They're in phase. But they're completely out of phase pi radians difference with the points in the loop next door. So you get this synchronized vibration, but no net energy actually travels down the string. It just sort of sloshes back and forth in place.
Fixed in space, but oscillating in time. Is there a mathematical way to capture that difference from a traveling wave? I feel like the math sometimes holds the key insight.
It absolutely does. If you do the math for combining two identical waves going opposite ways, you end up with a wave function like yx et e2 x xt. And the crucial part, the real aha moment, is that the space part, x, and the time part, t, are separated. See, in a traveling wave, they usually mix together like in a kx term. This separation tells you mathematically that the spatial shape, the 2 and kx part, is fixed. It doesn't move. The whole pattern just oscillates up and down in time, governed by the cos part. The energy stays localized. That's the mathematical signature of standing still.
And that sinks part directly gives you the nodes and antinodes.
Exactly. The sin cox term dictates where the amplitude is 0 the nodes and where it's maximum the antinodes. Plus, for this to even happen on something finite, like our string of length L fixed at both ends, you have boundary conditions. The ends can't move. Displacement must be 0 at x is 0 and Gexall. This forces a resonance condition. L has to be an integer multiple m of half wavelengths. L equals m. This is huge. It means only specific wavelengths, and therefore specific frequencies, the resonant frequencies or harmonics, are allowed. It's quantized.
Okay, that makes sense for a string. But how does this translate to light in a laser? Light's an electromagnetic wave, not a vibrating string.
The analogy holds remarkably well. Instead of physical displacement, what's oscillating in a laser is the strength of the electric and magnetic fields. But superposition still applies, and the highly reflective mirrors at each end of the laser cavity, they act just like those fixed ends of the string. For the electric field, the mirror surfaces must be nodes. The field strength has to be 0 right at the mirror.
So the light wave has to kind of fit perfectly between these mirror boundaries, just like the wave on the string.
Precisely. It forces the light to form an electromagnetic standing wave inside that cavity. And what's really amazing here is how these, relatively simple physics ideas, seen first with things like strings, end up dictating how something as complex as a laser operates. Honestly, this formation of electromagnetic standing waves, it's the absolute central principle behind how most lasers work.
That's a perfect segue. It brings us right into the laser cavity itself. This is where those standing waves live, so to speak.
Indeed. The optical cavity, or the Fabry-Pérot resonator, that's the heart of the laser. It does several critical jobs. It confines the photons, keeps them bouncing around. It provides feedback for the gain medium. That's the stuff that actually amplifies the light. And crucially for our discussion, it selects which frequencies and spatial patterns of light get to build up. Structurally, it's often just two mirrors facing each other, with that gain medium sitting in between.
And I remember there were different setups for the mirrors, right? Flat ones, curved ones.
That's right. You've got different geometries. Plane parallel is simple, but tricky to align. Confocal is very stable, gives you a nice tight beam. Concentric, hemispherical, various types. But whatever the geometry, the mirrors do two vital things. One, they make the light travel a really long, effective path through the gain medium, allowing for lots of amplification. Two, they establish those boundary conditions we talked about, forcing the electric field nodes right at their surfaces, setting the stage for standing waves.
Okay, so for the light to actually become a laser beam, that needs to resonate, it has to interfere constructively with itself, right?
Right.
Round trip after round trip. How does that work for light?
Yeah, it needs that positive reinforcement. For constructive interference, the phase change over one full round trip inside the cavity has to be an integer multiple of 2. Think about the path. Light goes from one mirror to the other and back. The optical path length for that round trip is 2nll is the cavity length, n is the refractive index inside. That distance, 2nl, must equal exactly an integer number, let's call it m, of wavelength, the lift. So the core resonance condition is muth at equals 2nl. Only light waves that meet this condition form stable standing waves. They get amplified. Everything else pretty much cancels itself out through destructive interference.
And this must a 2nl condition. This is what determines the specific colors, the frequencies that the laser puts out.
Absolutely. It directly leads to a discrete set of allowed frequencies. We call these the longitudinal modes. These are the standing wave patterns along the axis of the laser. The frequencies are given by m in AC to NL. Here, m is that big integer, often like 100,000 or even a million for typical lasers. C is light speed and index L length. And notice the spacing between adjacent modes, m and m+1, is constant. It's called the free spectral range, or FSR, and it's n EPOC2NL. So a laser doesn't emit a smooth spread of colors. It emits a comb, like the teeth on a comb, of very specific, sharp frequencies. These are the modes that fit the mate to 2NL rule and fall within the range of frequencies the gain medium can actually amplify.
It's not just about the frequency or color. Lasers have distinct beam shapes too, right? That's where transverse modes come in.
Exactly. Longitudinal modes tell you about the structure along the beam path. Transverse electromagnetic modes, or TEM modes, describe the pattern across the beam in the perpendicular plane. The ideal one, the one everyone usually wants, is the Taomura mode. It's the fundamental mode. No transverse nodes, just a single bright spot, most intense in the middle, fading out smoothly, a Gaussian profile, best beam quality. But you can also have higher order modes, like Taomura might have a dark line down the middle, splitting the beam into 2 lobes. Taomura could have 2 dark lines, making 4 spots. More complex patterns. Sometimes people write the full mode as TEM-MQ, where 10 and M describe the transverse pattern, and Q is basically that longitudinal mode number M we just talked about.
Okay, this brings up something that I think confuses a lot of people, myself included sometimes. We're talking about waves fitting perfectly, like mouse boost 2nL. But then we also talk about photons, these discrete particles of light. How do those two ideas work together inside a laser? What does this really mean for how we think about light?
That's a fantastic question, and it gets right to the heart of wave-particle duality. It's often an aha moment. It's tempting, but wrong, to think of a photon as a little ball bouncing back and forth. It's not quite right. A better analogy might be a musical note in a concert hall. That single note, that quantum of sound energy, doesn't just sit in one place. It fills the whole hall, defined by the hall's resonant structure, right? A photon in a laser cavity is similar. It's a single quantum of energy, yes, but it populates the entire standing wave mode. It's delocalized. Its location is described by that fixed standing wave probability pattern spread throughout the whole cavity. So the laser is this perfect example where you need both pictures. You need the particle idea, photons for energy exchange, pumping atoms up, stimulated emission, bringing them down. And you need the wave idea, standing waves, to explain the allowed frequencies and the shape of the beam. Both are essential.
That's a really clear way to put it. So standing waves are essential. They define the laser's light.
Yeah.
But they also bring problems. You mentioned a challenge earlier, spatial hole burning. Sounds ominous. This is where laser engineering gets tricky.
It does indeed. And to understand spatial hole burning, or SHB, we first need to talk about gain saturation. The gain medium, the laser's amplifier, doesn't have infinite amplification power. Gain depends on the population inversion having more atoms in the excited state than the lower state. Stimulated emission makes more light, which is good, but it uses up an excited atom, depleting the inversion. If the light inside the cavity gets intense enough, stimulated emission can happen faster than the pumping process can replenish the excited atoms. This reduces the gain, that's saturation. Basically, the more intense the light, the less effective the amplifier becomes for additional light.
Okay, so the amplifier gets sort of used up or tired where the light is strongest.
Exactly. Now, connect that to the standing wave. Inside a typical linear laser cavity, the light intensity isn't uniform, is it? It's really intense at the antinodes, where the electric field peaks. But it's zero at the nodes. So gain saturation happens unevenly. It gets heavily saturated near the antinodes, lots of stimulated emission depleting the excited atoms there. But at the nodes, no light intensity, no stimulated emission. The gain there remains high, unsaturated.
Ah, I see where this is going. The laser light itself is burning holes in the gain medium, but only where the light is strong, leaving untouched spots.
Precisely. That's spatial hole burning. You get this periodic pattern in the population inversion, mirroring the standing wave, but shifted. The lasing mode itself creates these regions of depleted gain at its antinodes and leaves behind regions of high available gain at its nodes. And here's the perverse part, as you called it earlier. This situation actually helps other potential laser modes. Another longitudinal mode with a slightly different frequency will have its standing wave pattern shifted slightly. Its antinodes might line up perfectly with the nodes of the first mode, where all that juicy, unsaturated gain is sitting, so the dominant mode inadvertently creates the perfect conditions for its competitors to start lasing too. It's like, well, self-sabotage.
Wow. Okay, that really is perverse. The laser makes it harder for itself and easier for other frequencies to jump in. This must have some really significant and probably annoying consequences for laser designers.
Yeah.
Why is SHB such a headache? What does it actually prevent?
Oh, it's a major headache. It causes several big problems. First, mode competition and multi-mode operation. SHB is the main reason why many lasers, even ones where you'd expect single frequency operation based on the gain medium alone, actually run on multiple longitudinal modes at once. That primary mode digs holes, and adjacent modes find enough gain in those holes to start up. This makes getting stable, single frequency output, what we call single longitudinal mode or SLM operation, really difficult.
And I bet the competition leads to things jumping around, being unstable.
Absolutely. You get fluctuations in the output power as modes compete. And you get mode hopping, where the laser suddenly jumps from lasing primarily on one frequency to another. In high-power semiconductor lasers, this isn't just annoying. The resulting fluctuations and stresses can actually damage the device, leading to degradation or even catastrophic failure. Second, there's power loss and inefficiency. All that population inversion sitting at the nodes of the standing wave, it's not being used efficiently by the main lasing mode. It's essentially wasted potential energy, reducing the overall efficiency of converting pump energy into laser light.
That really drives home the practical impact, especially for pushing laser power higher. How does SHB show up in, say, the numbers for high-power lasers?
In things like high-power semiconductor lasers, longitudinal SHB has very measurable effects. It leads to a higher effective threshold current. Because the carriers aren't distributed evenly, you get more spontaneous recombination in those high-gain node regions, acting like an extra loss. So you need to pump more current just to get the laser going. And maybe more importantly, it causes reduced slope efficiency. As you crank up the power, the gain saturation becomes more uneven. You need to pump even harder to overcome the fact that you're not efficiently extracting energy from the nodes. This acts like an increased internal loss and is a major limiting factor for how much power you can get out.
Okay, so it's a deep-seated problem tied directly to the standing wave itself. This naturally leads to the question, how do engineers fight back? What are the solutions?
Right, so engineers have come up with, broadly speaking, 3 main strategies to deal with SHB. 1, get rid of the standing wave altogether. 2, smooth out its intensity variations. Or 3, accept the standing wave but filter things so only one mode can win.
Okay, let's take strategy 1. Just eliminate the standing wave. How on earth do you do that if the mirrors inherently create them?
You change the fundamental geometry. Instead of a linear cavity, 2 mirrors facing each other, forcing back and forth reflection, you use a ring cavity. Think 3 or more mirrors forming a closed loop. Light can circulate around the ring clockwise or counterclockwise. the key difference. The forward-going beam and the backward-going beam travel mostly on different paths. They don't overlap everywhere to create that global standing wave pattern. They exist as independent traveling waves.
Ah, okay. Traveling waves, not standing waves. So no nodes, no antinodes, no SHB. But couldn't light travel both ways around the ring?
It could, and if it did, you might still get some standing wave effects where the beams do cross or interfere. So to truly eliminate SHB, you need unidirectional operation. You force the light to go only one way. This is usually done using an optical diode. It typically involves a Faraday rotator and some polarizers. The Faraday rotator twists the light's polarization differently depending on the direction it's traveling. This creates a small difference in loss for clockwise versus counterclockwise travel. Even a tiny loss difference is enough. Only the lower loss direction will reach threshold and laze. With only one traveling wave, the gain saturation is uniform, SHB is gone, and you naturally get very stable, single-frequency operation.
That sounds elegant. Great stability, narrow line width. What's the catch? Are they difficult to build?
They are generally more complex, yes. More mirrors mean trickier alignment that can be more expensive. And sometimes components like the Faraday isolator can limit the maximum achievable power. But for applications needing extreme stability and precision, think high-risk spectroscopy, metrology, laser gyroscopes, ring lasers are often the best choice.
Okay, strategy 1, go ring. Strategy 2 was homogenizing the standing wave, making it smoother. How does that work in a linear cavity?
This is the twisted mode technique. It's a clever trick for linear cavities. The goal is to make the total light intensity uniform across the gain medium, even though components of the light still form standing waves.
How do you manage that? Sounds like magic.
It feels a bit like it. You put a quarter-wave plate or four-plate at each end of the gain medium inside the cavity, and you rotate them by 45 degrees relative to the main polarization axis. So linearly polarized light enters the first plate, becomes circularly polarized, travels through the gain, hits the second plate, reflects, comes back through the second plate. The crucial bit is this. The setup ensures that the two perpendicular linear polarization components of the light, call them X and A, end up forming standing waves that are spatially shifted by a quarter wavelength relative to each other. So where the X standing wave has a peak antinode, the A standing wave has a zero node, and vice versa. Now, the total intensity is proportional to x squared plus I squared, x plus I cos. And since sin something plus cos something 1, if the two patterns are shifted like that, their sum is constant. It's uniform across the gain medium. It effectively washes out the nodes and antinodes in the total intensity profile, leading to uniform gain saturation.
Wow, that is clever. Using polarization to average out the bumps, are there limitations?
It works beautifully for many systems, enabling stable single-frequency operation in linear cavities where you might otherwise expect multi-mode behavior due to SHB. The main limitation is that it doesn't play well with gain media that are inherently sensitive to polarization, anisotropic gain. The technique relies on precise polarization control.
Okay, so we can eliminate the standing wave with a ring or smooth it out with twisted mode. What's the third approach? Filtering.
Right. Strategy 3 basically says, okay, SHB is going to happen, we accept that, but we'll make sure only one mode actually gets enough gain to lace. It involves putting frequency-selective elements inside the cavity.
And the simplest way to do that, I guess, is just make the cavity really, really short.
That's the most basic filter, yes. If you make the cavity length L very short, the free spectral range, FSR, well, C2NL, becomes very large. If the FSR is wider than the entire gain bandwidth of the laser material, then only one longitudinal mode can possibly get enough gain to oscillate. Simple as that. That's the principle behind many microchip lasers and VCSELs, vertical cavity surface emitting lasers. They have inherently short cavities. The downside, of course, is that a short cavity limits how much gain medium you can have, which fundamentally limits the output power.
So for higher power, you need more sophisticated filters inside the cavity.
Exactly. You use intracavity filters. A common one is the Fabry-Pérot echelon. Think of it as a small secondary resonator inside the main one, usually a thin plate with reflective coatings. It has its own very sharp transmission peaks at specific frequencies. By carefully tuning the echelon, maybe by tilting it slightly or changing its temperature, you line up one of its transmission peaks with the desired laser mode. That mode sees low loss and laces. All the other modes fall in the echelon's high loss regions and get suppressed.
Are there other types of filters used?
Oh, yes. For more demanding applications, volume Bragg gratings, VBGs, are fantastic. These are bits of glass with a permanent holographically written grating inside. They act like incredibly narrow-band filters, maybe filtering down to just 15 picometers, which is an astonishingly small wavelength range. Very robust, very precise. And in semiconductor lasers, the filter is often built right into the chip structure itself. Think DFB, distributed feedback lasers, with a grating along the active region, or DBR, distributed Bragg reflector lasers, with grating sections acting as mirrors. They provide built-in wavelength selection.
So it really comes down to this fundamental design choice for engineers, doesn't it? Tackle the root cause, the standing wave itself with rings or twisted modes, or manage the symptom, the multimode operation due to SHB with filters. The application really drives the decision.
That sums it up perfectly. It's a constant trade-off based on what you need the laser to do, how much complexity you can tolerate, and what it needs to cost. Performance, complexity, cost, the usual engineering triangle.
It's fascinating how much engineering effort goes into dealing with such a fundamental wave phenomenon. Which brings me back to something we touched on earlier, that wave-particle duality. The laser just seems like such a perfect stage for seeing that play out.
It really is. You have these standing wave modes, purely wave-like phenomena defined by interference and cavity boundaries. These are the allowed quantum states for the light field. But the energy in those modes comes in discrete packets, photons. The processes of pumping energy into the laser medium and stimulated emission getting it out are fundamentally particle-like interactions, exchanges of energy quanta. So that photon inside the laser, it's not a little ball, it's an excitation of a delocalized wave pattern. You absolutely need both descriptions, wave and particle, to understand how a laser works. It really makes you pause and think about the nature of light itself.
And these standing wave ideas, they're not just historical concepts, right? They're still critical in brand new cutting-edge laser designs.
Absolutely. Think about microresonators used for sensing. Tiny rings or disks where light circulates. They often use standing wave patterns created by counterpropagating light. The exact positions of the nodes and antinodes in those tiny standing waves are incredibly sensitive to anything that changes the refractive index nearby, like a molecule sticking to the surface. That's how they achieve ultrasensitive detection. Or look at VCSELs. We mentioned their short cavity gives them single longitudinal mode operation. But managing the transverse modes and the spatial hole burning effects across the beam's face is still a huge challenge. Engineers embed complex structures, like oxide layers, specifically to control the transverse standing wave patterns and optimize performance.
So if we had to boil it all down, what's the absolute core takeaway about standing waves and lasers?
I'd say the core idea is that standing waves aren't just present in linear laser cavities, they are the organizing principle. That simple condition, mu2 il L, is what dictates the allowed states of light, quantizing the field and defining the laser's specific frequencies and beam structure.
And the inescapable consequence.
Spatial hole burning. It's the direct and often problematic result of that standing wave intensity pattern interacting with the gain medium. It drives multi-mode behavior, instability, inefficiency, and therefore, a huge amount of clever laser engineering boils down to finding ways to overcome, sidestep, or manage the effects of SHB.
It really highlights the ingenuity, that dance between the fundamental physics and the practical engineering goals. Right. Eliminate, homogenize, filter.
Exactly. And understanding this interplay from basic superposition right up to inhomogeneous gain saturation is crucial for anyone designing or working with high-performance lasers, whether it's for cutting steel, sequencing DNA, or detecting gravitational waves.
So maybe the next time you encounter a laser beam, you won't just see a beam of light. Perhaps you'll picture those invisible, intricate patterns, the standing waves dancing inside, shaping the light we see. It's a hidden world dictating the visible one. Makes you wonder what other everyday things are governed by complex wave phenomena we don't usually see. Something to think about. We really hope this deep dive has given you a new appreciation for the physics inside the laser. Thanks for joining us on this exploration. We look forward to diving into another topic with you next time.